This is my first video that I'm creating on graphing linear equations that are in slope-intercept form, and how to do them more quickly than making a table of values every time you want to graph an equation that we do call a linear equation. So let's start with this. We say slope-intercept form of a linear equation, where the root word of linear is line, so we're graphing lines here. It's a line. We say is an equation considered to be in slope-intercept form if it can be written thusly. And we see we have here y equals mx plus b. So key characteristics, let's go ahead and point a few out here. We say y is isolated. So we say y isolated. This is kind of an important deal. We also notice on the right side here we have a number in front of our x. So we usually refer to this as the coefficient of a variable. We say coefficient of x. We have some constant here. We're going to say this is b as a constant. Okay. Other things we want to mention about this, and I kind of write this here. We'll explore why this is the case. But we say m is the slope. So we're going to go ahead and drop this in here. We say m is the slope, and we always use the letter m to denote slope, which is kind of a thing. And we say b is the y-intercept. So we say this is our y-intercept, and that's a fancy way of saying this is the y value where our graph hits the x or the y-axis. So we say graph hits the y-axis here. And that's what that value is going to tell us. Okay, so when we look at a linear equation, you notice that I have several written down here, and it's kind of easy to see that these are all in what we call a slope-intercept form, because all of the y's are isolated in each of the equations. Okay, if we look in each one of these also, we notice here that I have a number times x and a constant off on the right, and a number times x and a constant off on the right. These two down here look a little bit different. We'll talk about those when we get to them, but essentially we can see that all of these are of this form here, slope-intercept form. And I guess I could say this, we call it slope-intercept form because it tells us both the slope and the intercept of the equation. So moving forward with why we are talking about what we're talking about in this video, we say if I wanted to graph this linear equation, one way to do it is we could create a table of values. Okay, so this is a very easy thing to do. It's very straightforward every time. And we can see that we could plug in, since x is the independent variable, it could do whatever it wants. We could plug in whatever we want for x, independent values. But we will plug these in, and we see that we get when x is equal to -2, this is the same thing as, recall, f of x here. So what we want to do is we want to go find f of -2, or we want to find the function value or the y value when x equals -2. So recall that this means wherever we see an input, we need to go take it out. In other words, we're saying that this is the x value here, and all we're doing is substituting it in for the x value that we had in our rule. Okay? So good deal. We say if I substitute in a -2, we get -3 times -2 is a +6 plus 4, and we get 10. So this means that -2 comma 10 is a solution pair, and it also means that it's on our graph. Okay. So if we keep plugging in numbers here, for instance, if I say go find f of -1, which is our next x value here, we say -3 times -1 plus 4, which gives us 3 plus 4 is equal to 7. So I get -1 comma +7. Okay, we'll do one more here. 0 is very easy to plug in. I love plugging in or substituting 0, because anything times 0 is going to be 0, and we get, in this case, just 4. We just get this extra number off on the right here, this b thing. Okay, so we say 4. I'm actually going to stop right here and tell you, basically lines, we've seen these before, they're very, very predictable. And so every time x is going up by 1, every time x goes up by 1, you know, what's happening to our dependent variable, or our y value in this case. And we see that in this case it's decreasing by 3. Okay, and this, we've given this a name before. As a matter of fact, we've called this the change in y, or the change in x, or how fast y is changing with respect to x, which is called m. This is our slope. So we want to recognize that this right here, the way it's changing, is our slope. Okay, and so I could predict the next point here is going to be 1, the next one's going to be decreased by 3, another 3 here, and we say 2, -2. So we've got 5 ordered pairs that we can put on our graph, and this was kind of the older way of graphing. We say go left 2, I think this goes, let's see here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, notice that the top one here, 10, kind of goes off the grid here. We say -1, 7, oops, -1, 7, so we'd say here, and then it'd be down 3 from 10. So it's, I'm kind of going, you know, down 3, right 1, basically. We say down 3 from here, right 1. We see that we have the point 0, 4 on our graph, which is that point. If I went down 3, another right 1, I'd see the point 1, 1, which is right here. And then if I went down 3, another right 1. Okay, and so the whole intent of this video, and I'm going to go ahead and sketch in our line here, and we do want to label this. We say, we put arrows on it, we say this is the graph of y equals -3x plus 4. We could also call this f of x equals -3x plus 4. The thing about this is, since lines are so predictable, we can see that there are a few characteristics that are going to be on every graph. So I'm going to go back over here, I'm going to point out really quickly a few things. First thing is this, when we plugged in 0, we got the thing that we were multiplying by x to drop out completely, and all that was left was this b term. So another thing I want to say about this is that's just the point right here. We say 0 comma in this case 4. But we say we plugged in 0 for x, and the reason why we did so, well, I guess I don't want to say the reason why we did so, but you'll notice that this point, whenever the x value of a point is 0, you are some point that is on the y-axis. You are some point on this line x equals 0, which is a vertical line. Okay, but basically, if we wanted to find where our graph hits the y-axis, what we could do is we could plug in 0 for x and find y. The nifty thing about linear equations in slope-intercept form is that you notice every time you do that, you're just going to get this b value. So instead of having to make a table every time, one cool thing to tell you is whenever you plug in 0, you're always going to get the value of what this was right here, this b value. Okay, and so we could have recognized that b in this case was equal to 4 and said, look, I already know that it's going to hit my y-axis at 4. So that's one thing I want to draw from this. And the other thing I want to draw from this is this -3 here. You notice that it keeps going down by 3 every time. This is no mystery. It came from in our rule right here. We notice that every time we multiply -3 by a number that's 1 bigger than the number 4, or in other words, as x gets bigger, by 1 each time, this whole value is going to go down by 3 each time because I'm saying take -3 times that number. So this number right here is our slope, and remember that slope is rise over run. So we'd say not just -3, but -3 over 1, because this is our rise of -3 and run of positive 1. We always put the negative up top. So essentially, I could have known right off the bat that my graph hits the y-axis at this y value of 4 just by looking at the b value, and I could have known just by looking at this m value or slope value that my graph goes down 3, right 1, just by looking at it. Okay, so instead of having to make a table this time, when I look at something like this, you'll notice that making a table, I hope you notice, would be undesirable. I mean, I get to choose whatever x values I want, and of course, I could choose better x values than this. But we say when I plug in 0, I get 3/4 times 0. Minus 2, so I get -2. So I already noticed that this right here, this is our b value. I'm going to write it off on the side. We say b is -2. So we know that our graph hits at 0, -2, right here instantly. Okay, so now my slope in this case, I recognize that my slope is this coefficient of x is positive 3/4. This is my rise over my run. So I can use this from this point. I can go up 1, 2, 3. So I can go up 1, 2, 3, 1, 2. I'm trying to draw dots in here. And then run 4. And I noticed that I would get this point right here on my graph. Okay, this would actually be sufficient enough to draw every other solution point into this graph. We say this is the graph of y equals 3/4 x minus 2. But the thing I want to point out here, and this is the point, it looks like the point 4, 1. 4, 1 was our solution here. And this was the point 0, -2, of course. It's our 0b. But we could have just drawn this line very, very quickly just by looking at those things. Now, if I would have filled out this table, I want you to notice this. If I plug in 1, that's an easy number to take times anything, I would have gotten this. I would have gotten 3/4 times our x value minus 2. This would have been f of 1. Whoops, too many parentheses. And I would have taken this times 1, but then I would have gotten 3/4 minus 2, which, by the way, is -1 1/4, which nobody wants to deal with fractions unless they have to. Okay, so here's the deal. Graphing this out of just slope-intercept form by recognizing m and b is very quick. Let's go ahead and finish these last two out I said I was going to mention. We say, is this in slope-intercept form? Is this in y equals mx plus b form? And can I identify the slope and the y-intercept? Well, we say this is in slope-intercept form because the y is by itself. But you say, in this case, where's our x? And what I want to point out is it's 0 x's plus 3 constants. So in this case, we could say, we know this. We know our slope is 0, or 0 over 1, and we know our y-intercept is positive 3. So to graph this, we'd go up 3 on the y-axis. Remember, the y-intercept. So we say this is the point 0, 3. And then we say we would use our slope, which means I'm going to rise none but run 1, which means here's another dot. Rise none, run 1. Here's another dot. I could just keep doing this. As long as I keep using that slope, and so we'd say I get this here. So we say y equals 3, and one thing I want to point out about this is it's a horizontal line. Whenever you have y equals a constant, this is a horizontal line, always, because it has a slope of 0. Okay, in this last case, let's take a look at this line. You'll notice that our y-intercept's missing, our plus b. So we have our m here, our m value, our slope, but we were missing the b. But now we've identified that we could always tack on a 0. So we say m is -5/2, b is 0. So we know that it hits the y-axis at a height of 0. So we say this is the point 0, 0. You notice that we have a negative slope here. We're going to go down 5. 1, 2, 3, 4, 5. As I run 2, I could do this again. I say down 5, over 2. 10 kind of goes off the graph here. And then I could sketch in all the rest of the solutions, and we should label this. We call this like, f of x. Function of x equals -5/2 times the input value, this thing here. But essentially, a few other things to notice. You'll notice that any of these problems that had negative slopes, we were going down. Okay, so this has a negative slope. We say a negative slope here. This has a 0 slope, so you'd be standing on the ground. And this has a positive slope. Okay. Anyways, this is how you could quickly graph lines in slope-intercept form. Cheers.